Hi and welcome back. In this video lecture, we'll give some MPC Design guidelines for nonlinear systems. We start by considering the nonlinear system xt plus 1 is f of xt, ut. The system is subject to the constraints xt must remain within the set x uppercase, and the control actions ut must be taken from the set u uppercase. We assume that the origin is an equilibrium point of the system. This means that f at 0, 0 is equal to 0. We further assume that 0 is inside x and 0 is inside u. And lastly, we assume that f is differentiable with respect to both arguments, and it has a Lipschitz continuous Jacobian. This last assumption allows us to linearize function f, and in fact it allows us to write f as ax plus bu plus a linearization error that satisfies a certain bound. Now ax plus bu is the so-called linearization of f, and delta is the linearization error. Here a is the Jacobian of f with respect to x at the origin, and b is the Jacobian of f with respect to u at the origin. The linearization error delta satisfies the following bound. So the norm of delta is no larger than L times the squared norm of the vector x, u. Here L is a positive constant. We had stated that in handout number 2 and the corresponding slides, and it was stated as an exercise. If you go back there, you will be able to find a hint that will help you prove this. But this inequality comes from the assumption that f is differentiable with a Lipschitz continuous Jacobian. That's why we need it. And this inequality will play an essential role in our design. So the recipe we will follow is the following. First of all, we will choose a quadratic stage cost function. We will choose L to be 1/2 x transpose qx plus u transpose ru, where q and r are symmetric positive definite matrices. Then, second, we will choose a matrix K, which is a stabilizing gain for a, b. So we will find the matrix K so that a plus bk is a stable matrix. We will denote the corresponding controller by kappa. So kappa of x is k times x. And now if we apply that linear controller to the nonlinear system, we obtain the closed loop system with function f subscript kappa. So f kappa of x is f evaluated at x, kx. This is the nonlinear system with a linear controller. Now define a bar and q bar as before. So a bar is a plus bk, and q bar is q plus k transpose rk. The next step is to find a matrix P, which is symmetric and positive definite, that solves a Lyapunov equation. This Lyapunov equation is the following. It is P equals A bar transpose P A bar plus 2 times Q bar. And that's the main difference from the methodology for constrained linear systems. So here we have 2 times Q bar instead of just Q bar. So having computed this P, and there is a lot of software and algorithms we can use to determine this matrix P, we can define VF, we can define the terminal cost function, and we define it as 1/2 x transpose px. And then we define the terminal set of constraints xf to be a sublevel set of VF at level alpha half for some value of alpha. We will discuss how we will choose alpha. So now, once again, VF is a quadratic function of the form 1/2 x transpose p x with p computed as above, and xf is the set of all x in Rn such that VF of x is less than or equal alpha half. Alpha is positive and must be chosen to be appropriately small. We will explain. Now the procedure we will follow to determine alpha and also to prove that this choice of a VF and an X and XF is a viable one. It is a choice that can lead to the satisfaction of the stabilizing terminal conditions for MPC, the procedure is the following. First of all, we can very easily verify that f kappa of x can be written as a bar x plus delta of x comma kx. Here's what this means. It means that f kappa of x, the closed loop function with the application of the linear controller kappa, can be written out as a linear part a bar times x plus a nonlinear part. Now the next step is to try to understand how that nonlinear part, delta of x comma kx, how this nonlinear part grows as we move away from the origin. And then we will show that the norm of delta of x comma kx is less than or equal some constant L bar times the norm of x squared. So that will be the first step in our procedure. Afterwards, we will be able to show that Vf, as we defined it previously, satisfies a Lyapunov decrease condition for the closed loop system xt plus 1 is equal to f kappa of xt, and it satisfies such a Lyapunov decrease condition over a ball of radius eta for some appropriate eta. And afterwards, we will show that it is possible to choose alpha sufficiently small to squeeze xf inside that ball of radius eta. Then we will define x kappa, which is the set of all states x in x uppercase, such that kappa of x is inside u, so kx is inside u, and we will assume that 0 is in the interior of that set. The origin is contained in the interior of x kappa. The last step will be to find a sufficiently small alpha such that xf is squeezed inside x kappa, and at the same time xf is inside a ball of radius eta. We will do so now via a sequence of propositions. The first proposition goes as follows. We define the function delta bar of x, which is delta of x comma kx, and we can show that the norm of delta bar is less than or equal L bar times the squared norm of x. L bar here is equal to L times 1 plus the norm of k squared. The proof is in the slides if you would like to have a look and study it. The second proposition states the following. It says that Vf satisfies a Lyapunov decrease condition over a ball of radius eta. Eta is a scalar, it's a constant that is given by this equation you see here that involves L bar, the norm of A bar, the minimum eigenvalue of Q bar, and the maximum eigenvalue of P. The inequality states that Vf of f kappa of x minus Vf of x is less than or equal minus 1/2 x transpose Q bar x, and this holds for all x in a ball of radius eta. The proof is in the slides if you would like to have a closer look and study it. The third proposition states that if we choose alpha to be a positive number that does not exceed eta squared times the minimum eigenvalue of p, then xf, the terminal set xf, the sublevel set of Vf at level alpha half, is indeed a subset of the ball of radius eta. So we can choose alpha small enough to squeeze xf and put it inside, make it be a subset of the ball of radius eta. And what do we know about the ball of radius eta? We know that there Vf satisfies a Lyapunov decrease condition. Of course, this Lyapunov decrease condition will be satisfied inside the set xf. The last proposition, which is a result, comes from combining the last two propositions, states the following. It states that xf, as we defined it previously, so a sublevel set of Vf with alpha less than or equal eta squared times the minimum eigenvalue of p, is a positively invariant set for the system xt plus 1 is f kappa of xt. And once again, what is f kappa? It is the nonlinear system dynamics, f of x comma u with the application of the linear controller kappa of x, which is kx. Now, having stated these results, we can now once again write down the recipe for designing a stabilizing MPC. So we have this nonlinear system. Xt plus 1 is axt plus but plus delta of xt ut, where delta is the linearization error that satisfies a certain bound, which is norm of delta less than or equal L times the squared norm of x comma u. The system is subject to certain constraints. X belongs to x, u belongs to u. And let's take here, suppose that x and u have a certain form. They are, for example, polyhedra. They are polyhedral sets. Now choose L to be a quadratic stage cost. Choose a matrix K, which is a stabilizing gain for A, B. We haven't said so explicitly, but of course we assume that A, B must be a stabilizable pair. Otherwise, it will be impossible to find such a matrix K. Then define A bar and Q bar, the same way as we discussed before, and compute a matrix P that solves this Lyapunov equation. P is equal to A bar transpose P A bar plus 2 times Q bar. Don't forget about the 2. Compute eta via this equation. Choose this VF, which is 1/2 x transpose PX, and choose alpha to be a positive number, which is less than eta squared times the minimum eigenvalue of P, such that XF becomes a subset of X kappa. Now, how exactly can you choose alpha so that XF becomes a subset of X kappa? Let's have a look. What is XF? It is an ellipsoid. What about X kappa? Given that X and U are polyhedral sets, X kappa is also a polyhedron. Therefore, we're looking for a way to squeeze an ellipsoid inside a polyhedron. How do we do that? You can go back to the previous video lecture and see how we can put an ellipsoid inside the polyhedron. This is an exercise that you can solve to practice and give a formula for the maximum value of alpha that we can choose. We have stated a design methodology for nonlinear systems based on the local linearization, on the linearization of f at the origin. The main challenge remains how to solve the nonlinear optimal control problem that we have to solve in real time. So every time we need to use MPC, every time we need to compute a control action, we need to solve a non-convex optimization problem, a non-linear optimal control problem that involves nonlinear dynamics. From a computational point of view, this can be a very challenging problem, and it can be time-consuming and demanding in terms of computational resources. So that's the main challenge here. Also, there is one more thing. Eta and alpha can sometimes be very small in practice, and if that's the case, XF can be a very small set. This means that one would need to go for a very large prediction horizon to have a decently large domain of attraction. And the computation of Xn, the computation of the set of feasible states, is again a very difficult task. So there are many challenges around nonlinear MPC. One thing to have in mind, which is a significant difference between nonlinear MPC and linear MPC, is that inside the set XF, the controller kappa f, which is kx, the controller kappa of x we stated before, can be used. It's a controller that leads to local asymptotic stability and satisfaction of the constraints if we start from inside XF. However, it's not the same as kappa n star. Of course, it's not the same as the solution of the nonlinear MPC. The solution of a nonlinear optimal control problem is not given by a linear equation of the simple form k times x. We cannot expect that possibly. But if you remember, that was indeed the case in linear MPC. So if you remember, we had said that if we choose k and p to be the solutions of the infinite horizon optimal control problem, and then inside XF, the local terminal controller kappa F and the solution of the MPC coincide, but this doesn't happen in the case of nonlinear MPC. Now let's have a look at an example to put everything together and understand how things work in practice. We will give an example of an omnibot, a certain of a certain vehicle that we need to park. This omnibot can move in any direction on the two-dimensional plane and is towing a trailer. The position of the vehicle is denoted by x, y, and the orientation of the trailer is described by the angle theta. The system is controlled by velocity references, so there is a certain low-level controller that receives velocity references and sends out certain signals, voltages, to the motors to realize these velocities. The system dynamics is described by these three equations. There is one for the update of x, one for the update of y, and one for theta. There are a couple of constants involved, namely ts, which is the sampling time, and d, which is a distance. It is 80 centimeters, and the sampling time is 50 milliseconds. So it's quite a fast dynamical system. We have some constraints. So in particular, we require that the omnibot remains within a certain box. X and y must be in between -1 and 1, and the angle of the angle theta should not be less than -60 degrees or more than 60 degrees. Of course, we use radians in computations. The velocity references must remain within -0.2 and 0.2 for the x coordinate and -0.15 and 0.15 for the y coordinate. Now the system state is the vector x, y, and theta. And if we linearize the system dynamics, we will see that it can be written out as zt plus 1 is some matrix A times z times zt plus some matrix B times ut plus some linearization error. And for the linearization error, all we need to know is that its norm is less than or equal 0.6255 the squared times the squared norm of the vector z and u. And this is valid for all feasible z and u. So for all those vectors z and u that satisfy the constraints of the system. We choose a quadratic stage cost function. So L of z and u is 1/2 z transpose qz plus u transpose ru. And we select Q to be a diagonal matrix with positive diagonal entries, 1, 1, and 2. Apparently here, by choosing this matrix Q, we give more importance to how fast theta converges than x and y. And then we select the matrix R, which is equal to 10 times the identity. So it means also we give quite high significance to not actuating very aggressively. We need to keep the actuation low. We need to move smoothly and slowly, actually. I should rather say slowly from the initial point and orientation to the target point, which is the origin. We select K to be a stabilizing gain for the pair AB, and here, in fact, we determine K by solving an infinite horizon linear quadratic optimal control problem using the above Q and R. We find K by solving a discrete time algebraic Riccati equation. And then we determine a matrix P that solves this Lyapunov equation. And the matrix P is given here. It is symmetric and positive definite. Afterwards, we define VF to be 1/2 Z transpose P Z. Recall Z is the state of the system. And we can verify that the value of alpha, which is equal to 0.0118, satisfies the conditions of the guidelines we stated before. So first we determine eta, and then we determine an appropriate value of alpha. And this defines then the set XF. Now let's see some simulations in which we have used the prediction horizon n equals 60, so quite a long prediction horizon. We start from the initial state 0.5, minus 0.5, and 0.40 something, a little bit above 0.4, and we see that both the position and the pose is just a synonym for orientation. They converge gradually to the origin while respecting all the constraints that we have imposed on the system. Here we see the input, so the velocity references that we command to the system. We see also that these converge to 0 and they respect the constraints that we have imposed. And here we see the trajectory of the system as if we are looking at it from above, so that the trajectory of the system on the XY plane. And we see that it starts from the initial point and gradually converges and goes towards the target that is indicated with a red cross. Now, if you believe that this response is a bit slow and you want to speed it up, all you have to do is modify the entries of Q. So if you want to speed up how fast X and Y converge to 0, you can increase the weights, and instead of 1, you can put there 10. You see it is highlighted in blue, and that should speed things up. However, once you update Q, you need to update the matrix P, and of course recompute alpha. So this is the new matrix P, and this is the new value of alpha. In this simulation, you see with the dashed line, we are showing the previous simulation, and with the solid lines, we're showing the simulations with the modified matrix Q. And in fact, we can easily tell that the position converges faster towards 0. And of course, both the position and the pose satisfy the constraints that we have imposed. Same goes for the input. Again, the input satisfies also the constraints. We see that by increasing these coefficients in Q, we have made the system become more aggressive. And this is evident by the fact that the initial velocity, the velocity throughout the first few time instants, saturates at 0.2, which is one of the extreme values for U1, and minus 0.15, which is another extreme value for U2. And here we have the trajectory of the closed loop system from above. Once again, the dashed line is the previous simulation, and the solid white line is the new simulation. In both cases, the system respects the constraints and converges to the target. The last plot we see here shows V star 60 of the state of the system, which is like the energy of the system, and we see that this converges to 0. Recall that V star n, V star 60 in this case, serves as a Lyapunov function for the closed loop system. So thank you very much for watching, and actually this is everything. We have covered everything that is related to control in this module, and the next video lectures will be on probability theory and estimation theory. So goodbye.